So I figured we'd do a couple things today. Do some QA. I also have some guided demos I want to do, stuff that relates to some of the assignments. And yeah, that'll be that. But before we start, questions. How'd things go so far on the exercises? You're gonna have to forgive me a little bit today. I have this sinus headache. I get them sometimes especially when the weather changes. So I take sinus headache medication, but it makes me a little loopy. At least my head doesn't hurt now. But if I'm a little out of it today, that is why. So questions, how'd things go? Thanks, Thomas. A lot of syscalls in the exercises yesterday. Anything surprising or stuff that caught you off guard or? Several people are typing. While everybody's typing, I could point this out. I have this book. If this Unix system programming stuff is intriguing you, there's this book called Advanced Programming in the Unix Environment by W. Richard Stevens, the late W. Richard Stevens, a fantastic author who wrote tons and tons of books about Unix system programming. This book is awesome. And I would never suggest that you go look for a pirated PDF copy. I love KNR. That book, where is it? Funny, I've got a lot of books on my bookshelf. Ha! A copy of KNR somewhere. I knew it. This book is great. I like it. It's really small, it's concise, and it talks about all the basics of the language in a really straightforward way. According to the sticker, I bought this in December 1991. It's really the only C book I have on my bookshelf. There was another one by a guy named Peter van der Linden, I think, called Deep Sea Secrets. I thought that was a good book too. But if I were going to only buy one book, I would go with the C Programming Language by Kernahan and Ritchie, which is why it's called KNR. Sometimes the second edition is referred to as KNR 2. But Brian Kernahan, he is a really famous computer science guy, from Unix to C to book writing to he's written other languages. It's, yeah. You see him on Computer File all the time. Well, not all the time, but sometimes. And Dennis Ritchie, not all bad either. Also a famous computer scientist. So I definitely like those two books. Thomas's note about them doing the great experiment with the pipe and making the read happen before the write, and it just hung. Yeah, we should. I'm guessing that this experiment that you created a pipe and then you ran the read syscall and then the write syscall right afterwards, and it was just one process. Is that right, Vim? Wasn't it a child process? Or if it was a child process, it'll be a. Or you can have the parent right after the wait. Child try to read. Yeah, I'd be curious to see that source. The parent should write as long as it's not waiting for the child. But if the parent's waiting for the child, yeah, does the read block until the pipe gets the data? It totally does. I could do a little demo program for that right now because we haven't talked about what blocking even means. Let's see here. Where am I? Do I have something I can do here? Do we have Visual Studio Code open? Woohoo! All right, let's do a quick pipe demo and a blocking demo and see how this works. You guys can tell me what I'm leaving out of this. Let's take this and probably this and probably this. All right. So we're going to get a pair of file descriptors, and then I will call pipe to create the pipe with the file descriptor pair. So one file descriptor is the read end, and the other file descriptor is the write end of the pipe. And then let's try some fun stuff. So the working version of this, we should be able to write to one end of the pipe. Let's see, standard input, standard output. So we're writing to 1, right? Is this how it works? Tell me if I'm wrong. We're writing to 1 and we're reading from 0. Yeah, okay. So I'm gonna, oh man. What are all the arguments to write? Is it just 3? Am I doing this right? Yes, it says right there, buffer and the number of bytes. I'm gonna write 7 bytes so that I include the null terminator at the end. Hello, exclamation point 7. And then let's make a buffer here, 128 characters, and then we'll read. Did I do this right? I guess I'll find out in a second. So I'm thinking what we've done here is we made the pipe, we've poured hello into it, and then we're going to read, hopefully, hello out of it. And then let's print that out. Hello. All right, that's what I wanted to see. But what I'm going to do is I'm going to reverse these lines. So this kind of happened as I expected. The pipe was created, we put hello into the pipe, and then we read hello out of the pipe, and then we printed out what was in the buffer, which was hello, just like we wanted. I'm going to reverse these 2 lines, though. First, I'm going to try to read out of the pipe, and then I'm going to write to the pipe, which seems backwards, and it is, but let's see what happens. Nothing. Nothing happens. We're sitting here in a state called blocked. Well, we say we're blocked. The process state is actually asleep right now. Let's get another terminal here. And then we'll get out of here. I'm going to look for the word pipe. Oh, boo. That stupid pipe thing not working. Okay, that worked. I'm just trying to remember the commands for PS to get this to work. Here's my pipe process that's running right now. And sure enough, its status is asleep. So it's sitting there waiting to read something from that pipe. And we say that it's blocked on the read. And so read is a system call, of course. And like all system calls, as our program was executing line by line by line, when it runs a system call like read, our program stops running and hands control to the operating system, saying, hey, operating system, please do this for me. And so what the operating system did was it says, oh, it looks like you're trying to read from a pipe. Let me have a look at that pipe. So the operating system looks at the pipe and says, it's empty. There's nothing there. You know what? I'm just going to leave you asleep, and I'm going to schedule a different process to run. And as soon as some data arrives on that pipe for you, I swear I'll wake you right up and give it to you as a result of that read call. So our program hits this point. The operating system says, I would give you data back, but there is none, so you're just going to go to sleep. And we'll wake you up as soon as something's ready. But of course, it's never going to be there because we haven't called write yet. But we can make a child process and make this happen here. So so if we're the child, let's read this thing and print it out. And then I'll just go ahead and exit from the child. Otherwise, we're the parent and we'll write. I'm going to add some more helpful output here. Actually, this is a constant string. I can just use put s to print a string out. So child is waiting to read. Someone's only. And then the parent writes. Oh, I forgot. Put s automatically puts a new line at the end for you. Too many new lines. So the child says it's waiting to read, and then it prints hello. Let's do this. I'm going to do one more thing up here. I'm going to put the parent to sleep for 3 seconds. So this will just make the parent process go to sleep for 3 seconds. Remember how I was saying the child process goes to sleep when it calls read and gets blocked? You can actually just ask to be put to sleep. So sleep is a system call. And when you call it, the operating system will be like, oh, you want to go to sleep. All right, you go to sleep. I'll schedule someone else, and I'll wake you up in 3 seconds because that's what you asked for. So let's give this a run. So there we go. The child sat there blocked, waiting to read. The parent went to sleep for 3 seconds. And then the parent wrote to the pipe. The child got woken up by the operating system, got scheduled to run again, and printed out that data. Let's see, is there a way to figure out what FD1 is outside of the program? What do you mean by outside of the program? You mean like does that file descriptor exist? Oh, I see what you're saying. Is there a way like from like some external process to get to that file descriptor and write something to it? Not with the pipe system call. So the pipe, Okay, that's not entirely true, but I don't want to go out in the weeds too much. Uh, I think there's like a system call that does file descriptor passing between processes. I'm going to just say in general, no, there's not a way, but in specific, there might be a way. There are so in Unix, there are a bunch of different ways of communicating between processes. Pipes are one of them. But if you knew you were in a position where you would want to communicate between processes in such a way where you wanted to basically find out what FD1 was from outside the program, I would probably recommend a different inter-process communication mechanism, one that makes it easier to discover where to write to. So there's a thing in Unix called Unix sockets that makes it so that you can actually just look up on the file system. You can open a file that's basically the connection, and any process could open that file and make that happen. There's also something called a named pipe that is just like a pipe, but it actually has a file associated with it that you can open and write to. So there are a couple different options. Pipe is just, as we've been using it, is a little too under-featured to make that happen. Named pipe, yeah. Yeah, you actually have to make a special type of file on the file system using a command called make node, MKNOD, and you can use that to create a named pipe, and then processes can open that pipe and write into it and read from it. Let's see, Vim, is there a general picture to keep in mind to understand when something hangs versus errors out? Uh, so yeah, how could I describe this? So if something's hanging, like in my previous example where it was just blocked on read and it was never going to unblock, uh, the idea there is that the operating system has decided that there's nothing to do at the moment for that process, so it's just put it to sleep. So the general picture there to keep in mind is if the process is hanging, if it's just asleep, then the operating system has decided there is nothing to do with that particular system call that it's making right then. So if you've called read and you've been put to sleep, the operating system is saying, hey, you called read, but I got nothing for you to read, so you're asleep. That said, of course, blocking is not the only way a process could hang, right? You could write an infinite loop or something. It's just with an infinite loop, you would see the process hanging, but if you looked at it in the process table, you would see that it was not asleep. You would see that it was running in this infinite loop versus how we saw it block on the read. It was actually asleep at that point. And then versus errors out, uh, yeah, it's kind of an interesting question. We can go philosophical here and be like, is it, if it's hanging, is that an error in our program? Like clearly earlier when I had the read before the write, I had a structural error in my program that was causing it to hang. But I don't know. I think probably the big idea of the operating system not having anything for you to do is probably the one to keep in mind. I realize that was a meandering answer. Did it actually answer your question? Why does accessing an array out of bounds lead to an error, but accessing this buffer with nothing in it, why does it hang? Oh, so you mean why does it hang on the read? So They're kind of two different things. So to answer the second part first, when we're hanging on the read, even though there's nothing in the buffer, we are not accessing the buffer out of bounds. We're not accessing that array out of bounds. So this guy right here, when you refer to buff, we are, of course, referring to a pointer to the first element in this array. So we've got 128 chars out in this array here. So we've got that space allocated, and we're just telling read that this is the start of that space. And we're also telling it this is how big the space is, by the way. 128 bytes starting right here. So it doesn't actually ever go out of bounds. Read is smart enough to never read more than this many bytes. It can read less than that many bytes, like as we just saw, because it returned right away after reading only 7 bytes. But it won't read more than 128 because we passed that in as the maximum number of bytes to read. So it's not actually accessing this out of bounds at this point. And the reason it was hanging wasn't because the buffer was empty, it was because there was nothing in the pipe. Here, I've got another thing to munge up on this source code, but I figured I'd post this before I get rid of it. I have another experiment to try. Munge from, that's, I wonder how common the word munge is in regular usage. Let's see, what do I want to do for this demo? All right, I've got a string that's 10 bytes long there. I'm going to write that into the pipe. We're going to do a little experiment. So I've got an infinite loop here. I'm writing 10 bytes into the pipe. So what's going to happen here, do you guys think? I don't have a reader for this pipe at all. I'm just writing to it. Forever. Speculation? What could happen here? What are some of the options? Buffer overflow. Conceivable. What else we got? Or just runs out of memory. Also conceivable. Give it a run. I'm going to save the file, and then I'm going to build it, and then give it a run. Let's see, we're running pipe. There's pipe. Looks like we're asleep. It's just hanging here asleep. Oops, that was me typing an escape. Ignore that character. All right, if we're hanging here asleep, what does that mean? The pipe is full. The pipe doesn't feel so good. Yeah, the pipe is full. Seems like kind of an interesting question. Like, how big is a pipe? Is it infinitely big? Does it have fixed size? It looks like we wrote 65,530 bytes, and then it stopped. So I'm speculating probably that if we read something at this point, it would allow us to write more stuff into the pipe. But right now, it just seems to be full. Now, we haven't done computer architecture yet, but 65,530 is really close to a certain number that stands out for computer scientists. And that number is 65,536, which happens to be exactly 64 kilobytes. So it looks like the pipe holds 64 kilobytes. And what happens if we try to write to a full pipe is that our process blocks. It blocks on the write call. And so what's happened is this process has said to the operating system, hey, write this to this pipe. The operating system said, hey, guess what? That pipe's full, so I'm just going to put you to sleep. And as soon as somebody empties that pipe out a little bit, then I'll wake you back up and write those bytes in there for you. So that's what happens. Can we make the pipe bigger? I don't actually know. I'm sure there's a system-dependent answer for that. Let's see, Linux size of a pipe. Let's see, the capacity is 65,000 bytes. How big is it? Is it possible to change the size of a named pipe? It looks like in Linux it's based on the page buffer size, which is tunable. So in Linux, a pipe is exactly 16 memory pages, and you can control how big a page is at some point. Oh, no, you can use it with a, here we go. Oh, awesome. A bigger pipe. So the Linux man page has this to say. So you can use a system call called fcntl, which is file control. It looks like you can set the pipe size using that in Linux, but it's going to be something different in Mac OS. Probably the operating system dependent thing. Cool. Let's see here. Fork pipe shared output. I think that was all the stuff that I had to talk about on pipes, actually. I was going to do exactly this guided demo later on pipes, but here it is now. Are there any more pipe questions based on what we've done here and based on the assignment? JavaScript really does make programming easy in many ways. like I said a couple days ago, I think, was it? Or did I dream it? It's a lot of these things are, people get tired of the pain points of a certain programming language, and so they invent a new programming language to get rid of those pain points. And eventually, someday, someone will get tired of JavaScript's pain points. They'll invent a new language, and the process will continue. Pipe questions? I did actually write a guide about Unix interprocess communication, Beej's Guide to IPC, if you really wanted to know more. Yeah, it totally would. If we read some lines, then we could write more. I don't have a child process to do that, so the parent's going to block here. But I could make a child process easily enough. So we can make our child, and if we're the parent, let's do all the writing, and then we'll have the child do the reading. So if the PID is not 0, sorry, let's do greater than, just in case we get an error. If PID is greater than 0, then we're the parent. So the parent's going to do all that writing and get stuck. Let me see here. Let me get some good output here. So the parent's going to do that, and if we're the child, I'll have the child do some reading, but way more slowly. Let's see here. So I'm going to read. I'll have a buffer for this. I better actually only read 10 bytes at a time. So here we'll have the child slowly and by slowly, we'll put it to sleep to make sure it goes really slow. There we go. So I'm going to child, go to sleep. Remember my semicolons, wrong language. Child will go to sleep, then it'll read forever. Whereas the parent's going to be writing frantically into the thing. Read from FD1. Yeah, that's not going to work. I'm not seeing my child print out. Oh, because I don't have new lines afterwards. So it's getting overwritten immediately. How about that? Did see the parent continuing to write, though, every second. So every time the child reads 10 bytes, it gives the parent another chance to write another 10 bytes in there. Let's do this. Let's have the parent write 10 bytes and the child read 100 bytes once a second. This might also, oops, make things kind of interesting. All right. So now the child wakes up, reads 100 bytes out of the pipe, and suddenly the parent has room to write 100 more bytes. So the parent wakes up and writes 10 sets of 10 bytes in there before going back to sleep again and waiting for the child to wake up and free up that much more space in the pipe. Zaniness. So the process keeps running forever, which is nice. We've just got it set up so that one is producing data and the other is consuming data. And Unix is nice enough that when the pipe is full, the data producer just goes to sleep to wait for room for the pipe to free up. We didn't actually have to write any special case code for that. From the parent's perspective, we're just writing as fast as we possibly can into the pipe. And from the child's perspective, we're just waking up every second, reading 100 bytes out of it. So our code is pretty simple. The operating system is the one that's dealing with all like, okay, you need to go to sleep now. Now you can wake up. Now you have to go to sleep too, et cetera, et cetera. Yep, the size of the pipe is constant. We're just emptying it and filling it and keeping track of the total bytes at this point. So at first we saw that, at least on my computer, it stopped at 64K. The pipe was full. But now that we've added this child process to read stuff out of it, to empty it down a little bit, then the parent process can wake back up again and write stuff in there. Put S and printf. Put S is a really simple function. All it does is print strings out. That's all it does. It also adds a new line onto the end for you. Technically, put S is going to be a little bit faster than printf because it doesn't have to look for any format specifiers like %d or anything like that. It just takes the string, writes it out. Put S is really similar to the function we wrote yesterday, that print string function that we wrote. Put S is basically the same as that. Put S always writes to standard out, and standard out is usually the screen. Like I demoed yesterday, you can put standard out to different places. Like if I run pipe redirected to foo.txt, everything's still writing to standard out, just like it was before, but I've changed standard out to go to a different place. I've changed it to go into this file instead. So it's an interesting thing to wrap your head around. Like standard output is always file descriptor number 1 every time. And processes that want to write to standard output, it's convenient as human to think that, okay, that goes to the screen, because usually it does. But then it's also convenient to think, okay, it usually goes to the screen, but I can change it. And I can change it external to the program that's running. It's like, here I ran pipe and I redirected standard output into foo.txt. Pipe didn't know. It's blissfully unaware. Pipe's like, I'm writing to standard output. That's all I'm doing. And whatever you do with standard output, that's your business. I'm just going to write to standard output. Maybe you let it go to the screen. Maybe you redirect it to a file. I don't know, and I don't care. So pipe just writes to file descriptor 1. That's all. Let's see. Would it work infinitely if we exit from the child process? So if we exited the child process after a little while, the parent process would just block again, because the child process will have stopped consuming. Let's see. Let's limit the lifetime of the child process. Did I do that right? Well, x minus minus is greater than 0. The child's clearly not dying, though. What have I done wrong here? It's clearly right in front of me, but my sinus headache-addled brain is not. Did I not rebuild? Is that what it was? I thought I rebuilt. All right, the child, yeah, I didn't rebuild. The child hasn't lived long enough to even demonstrate this. let's try it again with having the child live a little longer. So the child should live for 6 seconds, and then the child exits, and the parent's just stuck blocking again. Parents like, oh, somebody was consuming the data before, but now they're not, so now the pipe is full again. Any other pipe-related questions? Dump more source code here at you guys. Oh yeah, x minus minus greater than 0. So it's doing kind of two things at once right here. X minus minus, this is a post decrement. So what's going to happen is first this comparison is going to get done. First, it's going to C is going to check to see if x is greater than 0, and then after it does that, it's going to decrement x. So x started off at 6. First, we're going to check is 6 greater than 0. Yes, it is. So we're going to go in the while loop. Second, we're going to decrement x down to 5. So post-decrement means we are going to subtract 1 from the variable after we finish processing the rest of the expression. Does that make sense? A counter to this, the opposite of this, is a pre-decrement. If you put the minus minus first, this means first subtract 1 from x, then look at the rest of the expression. So if we did this first, x would be 6, then we'd get here, we would decrement it to 5, then we would compare, is 5 greater than 0? Does that make sense, Mark? So I'm kind of cramming multiple things onto the line here. We're doing two things, comparing x to 0, and we're decrementing x. Yeah, there's all kinds of stuff that C programmers often cram into the same line, and kind of in unexpected ways to other developers. You might see something like this. This is an aside here. This is probably not the most common thing, but let's say we wanted to subtract 2 from x before we do this test. You might see something like this. Oops, minus equals 2, comma, C has this thing called the comma operator, of all things. So this is perfectly valid C right here. What this does is first it executes the leftmost expression, so it subtracts 2 from x. Then after the comma, it executes the next expression, x is greater than 0. And the value of the total expression is the same as the value of the last one after the comma. So the comma operator means basically do expression A, then expression B, then expression C, and the result of the total one is the last one we have in our comma list. So you can do crazy stuff like this in C too, that you might occasionally see with the comma operator. And it's idiomatic in C. C developers do it, but I've never seen a line like this in JavaScript, even though I'm pretty sure this is valid JavaScript too. Yeah, the comma is very similar to that, although a little less specialized, I would argue. Actually, let's pop into JS really fast right here. 1,2. Yeah, it totally works. So we can do an assignment like this in JavaScript. X equals 1, 2, 3, 4, 5. You've probably never seen a line of JS like that because it looks insane. X has a value of 1. Maybe that didn't work the way I thought it did. But X was going to have the value of 6 there. Maybe JS does things differently after all. I'll have to look at that later. But I digress. Comma operators. It was messing around with comma operators and like I think it was comma operators and post increment or pre-increment. I can't remember what we were doing. But on the complang C news group, we were exploring the spec, the C 1989 spec, and we found an ambiguity, which was kind of weird. Like messing around with this crazy contrived example with the comma operator and pre and post increment and decrement, we managed to find an expression where it wasn't clear what part of it would execute first based on the spec. And it was a kind of a cool find. Like a lot of super hardcore C geeks, I managed to stump them. And it was a neat thing to see. It was like a hole in the spec. And then we went and looked at the C99 spec, 10 years later, the new C spec, and that hole was gone. It was, somebody had figured out that there was ambiguity in the spec there, and they'd fixed it. I don't know, because we had discovered this well after the C99 spec had been released. We were just looking at the old spec to see what was there. Trippy stuff. When I was writing my book on C programming, I wanted to be an expert, so I was reading the spec very deeply to see exactly how things behaved. Pretty hardcore. You gotta want it. Anyway, okay. What are we doing? 10:06. I've got time for one more thing. Do we have any more questions on pipes? Any more pipe questions at all? I do want to take a break in about 10 minutes because I think we started at 1:15. But I wanted to, let's see here. Exec, it's coffee on fork. So I'm going to ask this poll right now. This is about the first module, Monday, Tuesday. One of those files was dealing with struct. Oops, I don't want to edit the title. And I want to know how far people got. It was after quicksort, so I know a lot of people stopped at quicksort. However, structs are used in the sprint challenge. So I kind of wanted to spend a couple of minutes going over them. All right, that's enough. We'll give it some coverage. But you know what? It's 10:08. Let's do it after a 5-minute break. Oh, there was an error in. Oh, I don't know. If there was, I should fix it. Let's see here. All right. Let's do a 5-minute break, and then we'll come back. I'll talk about structs a little bit and some other stuff I have in mind. I'll catch you guys then. All righty, everybody back? I could do some solution walkthrough, but I'm loath to do it for the rest of it today because there's still more of the day to get some of it done for people who haven't done it yet. Plus, it's just kind of an exploration sort of thing more than it's important to remember that the goal here is not really to become a C developer, but the goal here is to learn a different language and practice learning a different language. So the demo pieces that I'm putting together are meant to be similar to the solutions, but not exactly the solutions. Because again, it's not, the goal really isn't to have a solution to these exercises. It's more to learn the language and stretch your brain in that regard. We could have done any other language. We just wanted to do another language. But C had some certain benefits to it. One, it's similar to C++. If you ever get into that, it's like the basis for it. But two, it's on the other end of the high level, low level spectrum. It is totally hard to learn new things that you don't find interesting. I admit. It's a challenge to come up with curriculum that is 100% interesting to about 100% of the people 100% of the time. It's a big challenge and virtually impossible. And so if it's not interesting, it's I can try to bend it to make it more interesting for sure. But what I am hoping is that it's the process of learning the language that is sticking more than the language itself. It's extremely likely you'll end up in a job working in a language at some point that you've never used before. And good developers just pick them up. It's like, oh, I got to learn a new language. Okay, I'll go learn the new language. No big deal. I don't know if I told you guys that we once hired somebody to work in a framework and a language that that developer had never used before. But we knew this guy was a good developer. So we're like, okay, we know it's going to take like 2 to 4 weeks for you to pick this up, and we'll cover it. Yeah, and he did. He went and picked it up and wrote some really great stuff for us. Let's see. I do have a real world example of C, but I'm not sure how useful it is to look at. The Linux kernel is written entirely in C. And you can look through all the source code for it, like the stuff that we're talking about here. We can take a look at it. It's going to be fairly impenetrable. I mean, some of the structure that you're going to recognize, like we have a function here. Other things you won't recognize, like whatever the static keyword is, whatever the inline keyword is. But hey, here's a void function that does this. So it's kind of, there's a huge amount of source code in the Linux kernel. It's absolutely massive. And it's all C, every single bit of it. Another common place that it's used, embedded systems where memory is very limited. C is a great thing for that. If you want to install Node or Python on such a system, you're out of luck. There's just not enough room to store it there. But C will compile to very small binaries. Some of you may have looked at those and seen that it was It's relatively small, 8 kilobytes. But yeah, so looking through the source code for me, I'm like, well, I see kind of what it's doing, but it's somebody specialized in this clearly, and so these things have meanings that I don't fully understand. This code we're looking at here is the completely fair scheduler. So this is code that decides which process to run next out of all the processes that are asleep, or all the processes that are waiting to run. Rather, it decides which ones need to go. So some massive algorithm is in here. You can see by the size of the thumb how much source we actually have. We got there 10,000 lines for one little piece of the kernel. But let me see if there's some good solution-y stuff I can walk through. I did want to walk through that struct solution. Let me see what that looks like. Hang on a second. Pull up the repo. Okay, this is what I'm looking at here. This was from, I think, Tuesdays. And this stuff gets used in the sprint challenge tomorrow, which is why I want to talk about it today. So, with apologies to the people who've gotten through this, let me launch into this now. And we can talk about how the struct stuff works. So, for those of you who didn't get there, or maybe even those of you who did, when you look at this code, what does it remind you of? If anything. An object, really similar to your good old JavaScript object. And in fact, it behaves very similarly to that, except as you might guess, based on what's here, it's more strongly typed. So instead of having an object in JavaScript where you can just throw anything you want onto it, structs are far more limited. You can only put in the fields of these specific types, and that's it. You can't, on the fly, you can't add new fields to it. So it's pretty fixed compared to an object. Another thing you don't commonly see is methods. So on an object, you could have functions as properties on your object in JavaScript. You could have pointers to functions in a struct. It's just not very common to see in C. So let's see here. What was this assignment actually? Type def keyword, I guess it's going to say in our structs.c. So we want to define a person struct. Let's see here. Let me clone this guy altogether, and then we can just do this thing. See if we can do this right. I haven't looked at this assignment, maybe even ever, because I think it might have changed since the last time I was in it. So a couple things are happening on this line, actually, and they're getting munged together a little bit. we're defining a new structure, a new struct person, and we want to put some things in it. It should have fields name, age, height, and weight. Name, age, come on. So we need these fields in here. We're kind of cramming two things onto the same line here, like I said, though. I'm going to separate them out just for clarity. But what was there was kind of a shorthand. It's type def, sorry. Okay. So the two things that were happening here were, one, we were declaring a struct that we could use later as a type. And then here is this type def keyword that sets up an alias for one type to another. So this is saying, hey, whenever I say person as a type, I actually mean struct person instead. A contrived example for type def is something like this. Whenever I see a variable of type beej, that means I actually meant a variable of type int. Type def is just a way of aliasing a new type name for another type name. So technically the type of this structure is type struct person, but in order to not have to type the word struct over and over again, we are just making an alias so that whenever in our code we say person, we actually mean struct person. Just like in my contrived example, wherever I said beej, I actually meant int. So a way of making new type names is type def. And you can see in the code here, we actually use the word person here as the type. And that makes sense because we've type defed it here in the structure. I know that's a little bit weird. The main thing is to remember is that this is just making it so the type person is the same as the type struct person. But as we saw earlier, we have to give types to these things. We can't just have fields here in the structure without types. So what type is everything? We kind of have a couple options for name. One of these. What type should name be? Make it a char. Although if it's a char, that means it's just one character. If it's a char pointer, it can point to a whole string. So that might be better. Another option here is to make it an array of chars. You can put that in there as well. But I'm not actually sure right now how it's intended to be used. Should it be a pointer or an array? We might have to look and see how it's used later to see exactly which one it should be. But I'm going to leave it as a pointer for now. All right, age, weight, and height. These all seem to be pretty inty to me. All right, so here we're defining a function called create person. Looks like we're going to call it here, create person Tony Stark, with an age, weight, or age, height, and weight. I'm like, he only weighs 64 pounds? Okay. All right. Actually, 64 doesn't make any sense in any case, does it? Oh, I guess it does. He's short-ish. 5'4". Is Tony Stark really 5'4"? Anyhow, so we want to create a person. So, and then we want to return a pointer to that person. We're going to do a couple different things here that one of them you might not have seen yet either if you didn't get past didn't get past quicksort. Oh, my brain today. Notice we want to return a pointer to a person. So we might be tempted to do something like this. Make a new person in here, and then say the person's name is name, and so on. And this is looking probably kind of similar to some of the stuff that you've done. Without the suit. You've probably written constructors or functions that have made a new object and taken parameters like this and used them to fill out object properties like that. So you might be tempted to do something like this. But there are several problems that we have to overcome here first. This isn't going to build as it is. For one thing, we want to return a pointer to a person. As it says here, the return type is a person pointer. But we're not actually returning that here. We're returning a person. So your second thought to fix it up might be something along these lines. Well, let's change this from the person to the pointer to the person. We'll use the address of and make that happen. So now that seems kind of sensible. We've got a person here. We've filled out the fields. We've returned a pointer to that person. That should technically create a person, right? But there's something wrong here. Does anybody know what it is? It's subtle. The real misery of this is that it'll probably work, but we're actually engaging in undefined behavior here. So this probably will work on your system, but it might crash, it might do anything. Let me ask a follow-up question. If I declare an integer here, what happens to that integer after this function returns? It goes away. It's just gone. Every local variable in C goes away after the function returns, including this person right here. There's no sense of closure. There's no garbage collection. So we kind of touched on this a couple days ago. Since C doesn't do garbage collection, basically the only thing it does is as soon as variables fall out of scope, as soon as the function returns, all those variables get destroyed. So we'll return a pointer to that person, but that pointer won't actually be valid anymore. It'll point to someplace in memory where that person was, but there's no guarantee that that person will still be there. We have to assume that it is not. What we need is a way to allocate memory for a new person that's persistent. We need a way to allocate memory that sticks around after this function returns. And fortunately, C provides us with a way to do that. Called malloc, memory allocate. This gives us some memory that's in a kind of a different place. Now, the C specification doesn't actually talk about these two terms I'm going to bring up right now, but as far as I know, every popular implementation of C uses them. So we're going to split up memory into two things. One of them is going to be called the stack, and the other is going to be called the heap. And the stack is a place where all the local variables go, like X and person, also where all the parameters go, like name, age, height, and weight. All that goes on the stack. And the stack is used to temporarily allocate memory as needed for functions. So this function, create person, needs some temporary memory. It needs something to hold name, age, height, and weight, x, and p. So it allocates that space on the stack. And when it returns, that space gets deallocated from the stack. The heap is more permanent. The heap you only allocate to explicitly and deallocate from explicitly. So nothing will get stored on the heap unless you do it, and nothing will get freed from the heap unless you do it. So in order to store something on the heap, we use malloc to allocate space on the heap to store that thing. We have to tell malloc how many bytes we wish to allocate. Size of is really helpful there, because size of tells you how many bytes big a structure is, for example. And then it returns a void pointer. Where's my man page? Malloc. It takes a size in bytes. It returns a void pointer, which means that pointer can automatically be converted into any other pointer type. So I'm going to change this code up a little bit. We're going to use malloc to allocate a number of bytes for a person, and then we'll have that space on the heap, and it won't go away after the function returns. I'm reluctant. So yes on the stack, and I'm a little hesitant on the heap versus closure. I'd probably want to say that the heap is more similar to, like, well, it is, I think. How about closure slash globals, maybe? I don't like globals either. That's kind of a bad way to put it. I'm not actually sure what the if it's a closure, it can't store it on the stack. It has to store it elsewhere, right? So maybe it is similar. I'm not actually sure how JavaScript does its closures under the hood, so this is why I'm hesitant. Something to research, though. So let's allocate a new person. Instead of using a person here, I'm going to get a pointer to a person, and I'm going to malloc that space like this. We need to give it the number of bytes we wish to malloc, and so I'm going to use size of to figure out how many bytes we need. Since I want to store a person, which is one of these structures here, I'm going to use size of to figure out how big that is, get that many bytes. Malloc will return a pointer to that chunk of memory we just allocated, and then we can store stuff in it. But now we have another syntactical problem. Oh, also on the return, we don't have to return the address of P anymore because it's already a pointer. So we'll just return P straight up. But we have a slightly different problem here now. Yeah, Thomas is leading ahead on it. The dot operator works on structures, but we don't have a structure here anymore in P. We have a pointer to a structure. So for the dot operator to work, we have two options. I'm going to show you the one nobody uses first. We can dereference like that. Now we're good on this line. We've dereferenced P. It was a pointer to a structure. We dereferenced it. Now it's a structure. Now we can use the arrow, or we can use the dot operator right here. But this visually is kind of clunky. Totally works, is totally valid, and does what we wanted to do. We want to dereference P and then use the dot operator. But the designers of the language decided that maybe we should add some syntactic sugar here. So we don't have to type this ugly line. Let's make it so that you can type this instead. So these two lines I have highlighted are exactly equivalent. So the general rule is in C, if you have a pointer to a structure, use the arrow operator to access its fields. And if you have a structure that's not a pointer, just a plain old structure, then use the dot operator to access its fields. In this case, we have a pointer to a structure, so I'm going to go ahead and use the arrow operator to access all those fields. That was a lot of stuff in one function. We learned about structs. We learned about allocating space. We learned about the arrow operator when you have a pointer to a struct to get the fields out versus the dot operator when you don't have a pointer to a struct. malloc is totally comparable to the new operator in C++. Yep. Very, very similar. And in many ways, similar to the new operator in JavaScript, for that matter. It's just that JavaScript is good at figuring out when to free that data that you allocated. JavaScript figures that out on its own with its garbage collector. So because name is pointer, we don't have to do anything special. Yep, that's a good question. We just have a char pointer name here and a char pointer name here. So since they're both pointers to chars, this assignment works out just fine. But there is, so something that C is not explicit about, but you have to keep in mind is who actually kind of owns that pointer. Like, what if somebody called create person with a temporary buffer that they later overwrote or that they later freed or something, and they just gave us a pointer to the buffer? Does it make sense that we just keep a pointer? Maybe the stuff that pointer points to changes later behind our back, and we didn't want that to happen or something. Some people might argue here, instead of copying the pointer, we should actually allocate more space and make a copy of the whole string. Like make a copy of the whole name instead of just putting another pointer to the same name. Might be a little safer. Just in case the caller decides to change the stuff that is at this address later. But that seems like that should have worked too. Did it not work, Thomas? Well, that's in the solution, actually. Everybody use string dupe. Does it say to do that in here? Oh, it says to do it. Read the instructions, Beach. Remember how I'm always telling you guys to read the instructions? All right, string dupe. Let's do that. String dip. Even better. All right. It says he has somewhere. It says it right here in the comment. That's embarrassing. Okay. Person destroy. Given a pointer to a person struct, free up the memory that holds the person's name as well as the memory that holds the person instance. String dupe. No, that's in lib somewhere. So string dupe undoubtedly does a malloc and allocates some space for the new string. So we've got to free that up. And we also want to free up the person that we allocated. So we're going to pass in this person pointer, and we want to free that person. And so the opposite of malloc is free, and we'll free the person. We also want to free the person's name because we allocated some space there with string dupe. But I've done something wrong here. What have I done wrong? What's my mistake? Yeah, I'm freeing the name before the person. I'm freeing the person before the name here. So technically, after I free who, we're not allowed to use who anymore. That thing's been deallocated. But then here I go and do it. I use who arrow name right on the next line. So the right way to do this is the other way around. First free the fields within the structure, then go back and free the structure. Oh, I love that question, Mark. That's awesome. Does that leave the age, height, and weight? What happened to those? I mean, we had to deallocate the person, we had to deallocate the name, but what about the rest of these things? How does that work? Uh, so, what's the best way to answer this question? I'm going to take two approaches to it. One, you only need to free things that you've mallocked. So if you didn't malloc it, you don't need to free it. And in fact, you can't free it actually. So that's one way to look at it. Like, did I malloc this thing? If I did, then I should free it. If I didn't malloc it, then I shouldn't. So there are two mallocs here. One of them is the main one we did for the person, and there's a malloc inside string dupe that allocates space for the string. So those are two mallocs, so we got to have the two frees for those mallocs. The way that height and weight and age actually get freed is that they are part of the person. So the person has several parts in it. It's got name, age, height, and weight. So it's got these four fields, and they all have values. Name points to something, age is some value, height is some value, and weight is some value. So all four of these fields get freed when you free the person. The tricky bit is that one of these fields, name, also points to a thing that needs to get freed. So we need to do that as well. That's why we got the extra, the free in there, and why name seemed like a special case. But all four of these fields themselves, they get freed up when you free the person itself. If we didn't do the free who arrow name right here, we just freed the person, then age, height, weight, name would all be destroyed, but the actual memory that was allocated for that name that's floating around out there in the heap, that would just remain out there as a memory leak. Does that make sense, Mark? I feel like I'm kind of bouncing around the answer a little bit. Thomas's question, is that extraneous? Yes, it is extraneous, but let me show you exactly why. Free. Where is it? The free function will deallocate the memory associated with pointer. If pointer is a null pointer, no operation is performed. So free ignores it if you pass null in. So you can safely free null, nothing will happen. That was it for the struct thing, right? And let's make test. We do this right? That doesn't seem right. Is this supposed to do something else? Person create, person destroy. The test file, like in tests, is there one over there? It's been too long since I've looked at this. Trying to remember how all the testing stuff works. The dumb part is that I helped write this test stuff, so I should remember. Should print out this. Should print out the struct. Oh, boo. Run some asserts. Oh, if I run it outright, all right. If I run it outright, it runs. I see. I see. Coming back to me now. Let's see. If we did p arrow name equals name without the string dupe, would we still have to free it independently? No. That's a great question, Austin. This ties back to like the question of who owns what. What is the ownership of this string? And like I said, C doesn't actually track ownership explicitly. Language like Rust is really big on that. Rust really keeps track of which piece of code owns a certain pointer at a certain time. But let's say we didn't do this. Oops. Again, back to our rule. If we didn't malloc it, we don't free it. So in this case, we would not free that thing because we didn't malloc it. And in this case, it looks like everything is probably going to work just fine because the string we pass in is a constant string. That's never going to change ever. So I'll bet we're all good there. But let me show an example of how this might go strangely. Let's see, create person, and I print the person later. So check this out. Let's make a buffer here of 128 characters. I'm going to initialize this buffer to Tony Stark. And we're going to pass this in as the person's name. So far, so good. Make it, we're all happy. And then I'm going to do this. So that's going to change what this was. This was Tony Stark. Now it's going to be asterisk Oni Stark. We've already created the person, though. So we call it create person. We got our person structure. We're like, yeah, person structure has Tony Stark in it. No problem. But then when we go to print it out later, we find that it's been changed. Somebody has messed with the data that we were pointing at. Blah. And so this is one of those cases where after create person, maybe we thought that this Tony pointer right here owned that data, but clearly somebody else manipulated it behind our back so that when we went to print it later, we ran into trouble. So in order to avoid that, be like, okay, you said you were Tony Stark to start with. We're going to make a copy of that. String dupe. So we have our own copy of Tony Stark. Now, if you mess with your copy of that later, that's your own business. We got our copy as it was at the time. So now we're back to normal, even though the original buffer has been adulterated here, munged. We've got our own copy of it now. Our copy doesn't get changed, and we print out Tony Stark. So there's no real hard and fast rule there. In some cases, it is safe to copy just the pointer. And if you're sure that it's never going to change later, then just copy the pointer. It's way faster to copy a pointer than it is to copy a string. Copying a pointer is an order 1 operation. Copying a string is an order n operation. So whenever possible, copy the pointer. But as I've demonstrated here was a case where copying the pointer allowed some badness to happen. If we munged the age or others, would the same thing happen? This is also a good question. And the answer is no, because a copy is being made of that already. So let's say we had age equals 64. And we put this here, age. What happens is that when we call create person, a copy of age gets made as this parameter right here. Remember, every parameter that gets passed to a function is a copy of the value that was passed in. So right here, we already have a copy of age. Not only that, but we copy it again here. So we got copies all over the place. It's confusing because it's similar to what we're doing with name. We've got copies of name all over the place, but there's only one chunk of memory that name points to. So we've got this, we've got name here, we've got p arrow name here. They're both pointing to the same chunk of memory. They're copies of one another. They're pointing to the same chunk of memory though, and there's only one of those chunks of memory. Pointers are a little weird that way. Yes. And I would say that keeping in mind while using pointers is the right thing. But another thing to keep clear in your head is that there's only one copy of that memory out there, and all the pointers are pointing to it. So I've got, let's see, let me take out my stir-dupe again. So we're using the pointer again. And we've got this buffer with Tony Stark in it. I'm going to draw that visually right here. So Tony Stark. So somewhere in memory, we've got this array of bytes. And we have a number of things that are actually pointing to it. One of them is buff out here in main. So buff points at this thing right here. And then when we call create person, we pass buff in as that parameter. Buff gets copied into another pointer called name. And name also points at that because name is a copy of buff. But we still only have one copy of Tony Stark in memory. Later on, right here in the code, p arrow name gets to be a copy of name. So it also points at Tony Stark. So at this point in the code, we've got 3 copies of this pointer. They're all pointing at the same place. Just like at this point in the code, we have 3 copies of age. They all have the same value. It's just things are simpler with age because a value is just a value. It doesn't point to any other additional data anywhere. It's simply however old Tony Stark was. It's simply 64. 64? Oh, that's his height. Oh, man. I got his age and his height mixed up. That's okay. My point stands. Yeah, so when we're copying those pointers, we're not copying the data that it points to. We're simply copying the value in the pointer. Remember, a pointer is just an index into memory. It's just a number. So we're copying the number around. We're saying Tony Stark's at address 398. So buff is 398. Name gets copied. Name is 398. P arrow name is 398. All of those are the address of T. Oh, let me look at the sprint challenge. you guys have a copy of the Sprint Challenge yet? Is that in Training Kit? Oh, Sprint Challenge something. Look at all these Sprint Challenges. Is it in Training Kit? Let me look. Training Kit, sometimes the rendering changes from what I remember. So objective Sprint Challenge. Yeah, it's there. All right. Let's see. I do have one more thing I can tell you about structs that will help with the Sprint Challenge. This one's pretty minor, but it has to do with the types. We were using type def to redefine structures. Let me see here. Let's close this. I just want to point out that it's also really common to not use type def with structures, and a lot of examples that you'll find will not use it. So we had a struct person before, but some people just declare like a struct animal. Let's see, chart pointer name. It's whoa. Thank you, autocomplete. That's exactly what I wanted to type. So some people don't even bother with the type def. They just make a new type called struct animal, and then they refer to that in their code all over the place. Struct animal pointer create animal. So same as we did before with the person, except this is the entire name of the type right here. The return type from this function is struct animal pointer. So it gets a little bit verbose, which is why sometimes people use type def to get rid of the verbosity of it. But I just wanted to point out that this is a really common thing in C, to just refer to it by the full name. Twelve-legged animal. Ugh. Again, this is the whole type right here, struct animal. Even though there's a space in there, that's the type name. So a lot of the examples you'll see with the Sprint Challenge tomorrow are going to have that style, using the word struct instead of using a type def. Does that make sense? Or is it confusing? Silence. Let me put it this way too. If we did this, I'm going to give this some crazy name, just so that it stands out a mile. If we did this, then we would be able to do something like this. Remember I said type def is making a new type name for an existing type. So I've made a new type called Baz. That's exactly the same as a struct animal. I can tell if that's helping or hindering. My main takeaway here is that struct animal is a type, and that you can declare variables of that type. So if we're good with that, then I'm happy. Yes, you can. After you make a new type alias with typedef, you can refer to either one. Oh, let's see, sprint challenge. Did I have that open? I thought I had that open. Let's bring this up. Oh, it was right there. I knew I had it open. So this code for tomorrow mixes a couple things. It mixes some system calls that you've never seen before with some C that you will have seen before. And the idea is to write a directory listing program, something that prints out directories just like ls does, except ours is going to be called ls, and it'll be a lot simpler. So there are some system calls, open dir and read dir and close dir, that will give you access to stuff that's in a directory. But when you read dir, it's going to return a structure to you, pointer to a structure. And that structure is going to have a couple things in it. One of them is going to be the file name. So the idea is we're going to open the directory. We're going to repeatedly read from it. And every time we read it, we're going to look at the return structure. We're going to print out the name of the file. So that's the gist of it. And then we've got a couple stretch goals here that pretty much double the size of the thing. The code itself for the MVP is probably about, I don't know, 50 lines long or something. It's not entirely huge. The biggest challenge is figuring out how to use these three system calls. And there are a lot of examples online. So I think this one's pretty straightforward. The stretch goals get more interesting. The second stretch goal is to print out a directory listing that shows things that are directories with the word dir next to them. So I don't think you'll run out of stuff to do. Oh, geez, I'm over time. So I think the plan for tomorrow, we'll go over a solution for the sprint challenge, and I will also tomorrow go over more solution stuff from the assignment today. But today is finish up that stuff from the processes repo, and also finish up anything from the Monday, Tuesday repo, although go ahead and push off quicksort until last if you're stuck on quicksort. Tomorrow at 12. Yeah, it's usually 12. Let me look at the calendar right here. Make sure there's nothing tomorrow at 12. Yes, I have nothing tomorrow at 12. It's kind of weirded me out. I feel like I should have something, but I guess I don't. All right. So yeah, tomorrow at 12. Oh, the typedef snippet. Let's see. Did I close that? And just this one, or oh, the animal thing. I just didn't have a type def in there. I've taken out that type def. I can put it back though. There we go. And while I'm here, we might as well do this one. This was structs from Tuesday. Cool. Anything else, gang? Sorry for the overrun. I do readily admit that C is not for everybody, as much as it pains me to say. Again, I would stress, remember that this is about learning a new language more than anything else, and the skills that you pick up while learning a new language are really useful in learning additional new languages in the future, something you definitely will do. But yeah, as much as I try to be interested in everything in computer science, there just are some things that are just they just don't grip me. But that's okay. There's a lot of stuff out there. All right, gang. I'll post this video as soon as I can. Everybody have a good lunch, and let me know if you have any questions. See y'all.